Today we are going to discuss a paradigm shift in the furnace longevity. We are moving towards a unified approach that integrate real-time operational taphole analytics with next-generation structural refractory monitoring. Based on data from a 7,000 TPD furnace, we will show how operational execution directly serves as the first line of defense for the hearth structure. The challenge is clear. The hearth dictates the entire furnace life. Degradation happens on two fronts. The first, fluid dynamics, where uneven liquid level and poor deadman permeability alter gas flow and risk the furnace freezing and choking. Second is the structural stress, where zinc and alkali chemical attack combined with extreme thermal load erode refractory bricks severely, as it's shown very clearly in the slide, the both pillars. Proper taphole management is the only way to maintain the stability required to avoid the premature costly relining. Thus, why this is important, that is going to summarize in the subsequent slides. To meet this challenge, our strategies stand on two pillars. Pillar one is operational optimization, which is focus on purely drainage management using casthouse historic data like drainage time, mudgun consumption, workmanship, application of the clay in the taphole spool, and so many things. As far pillar 2 is concerned, it is limited to structural monitoring, utilizing Acousto-Ultrasonic Echo, that is AUE, and 2D thermal models for proactive wear verification. And just in earlier presentation, also a part of it has been discussed. Together, these pillars moves us from reactive maintenance to unprecedented campaign longevity, and how it is getting done is going to explain to take a cover of all those topics in the upcoming slides. So we manage the pillar 1 through a 16 parameter evaluation dashboard. We are not just looking at production, we are tracking precise target, campaign duration of 26 to 30 days, drainage times between 170 190 minutes, and maintaining taphole length between 3 to 3.4 that is meters. So, uh, so by monitoring the deviation in the mud injection and slag retention, we can grade the success rate of every campaign with total objectivity. Now coming to the optimizing casthouse operation, which is supposed to be one of the major activity in achieving those targets. But how do we hit these numbers as shown? So it requires three operational discipline. And what are they? The first one is the consistent use of 55 millimeter drill diameter, utilizing mud with a high extrusion index for superior sealing, and minimizing the operational procedure correction, considering fluid flow protect the inner hearth boundary, directly linking our daily casthouse discipline to the structural survival of the furnace. Now coming to the pillar number 2. While we optimize the operation, we must also improve how we see the refractory. Legacy 1D thermal modeling relies on the flawed assumption of uniform heat transfer. The hidden reality is more complex. Thermal inertia masks short-term changes, the elephant foot effect, which creates a critical wear in the bottom corner, and the chemical degradation can reduce the thermal conductivity by roughly 66%. 66% is a big value. And once temperature exceed 850 degrees centigrade, this activity goes in a very accelerated form. Now, our solution is to combine Acousto-Ultrasonic Echo with the 2D thermal mapping. That is, AUE uses stress waves to detect boundary anomalies and refractory thickness without stopping production. By pinning the structural boundary with this NDT result, we eliminate the blind spot of the thermocouple only and only models which are allowing for precise prediction of protective skull thickness and chemically attacked zones are going to have a lot of implication on the outcomes. So a critical insight from our 2D modeling is shared, which shows that the sensor depth gap. So in a skull loss event, a deep sensor catches the anomaly and reaches 95% of its steady state reading in just 1 hour. A shallow sensor suppressed by the hearth thermal mass can take over 4 hours to respond. This means poorly placed shallow sensor can completely miss temporary skull loss event that threaten the furnace shell. And this tells a big loophole while installing these sensors in the capital buildup of the furnace. So all these things are to be taken into deep consideration while going for this capital buildup of the blast furnace. Now this matrix shows how to model work in synergy. The taphole evaluation model provides the proactive prevention by tracking the daily operational data to grade campaign success. The AUE and thermal wear model, which we had talked earlier, which provides the proactive verification by generating 2D wear profile and isotherm maps. So we use intervention triggers like mud injection deviation or acoustic boundary shift to adjust our strategy in real time. In conclusion, our clear deliverables is the implementation of the hearth stability loop. We optimize taphole execution to ensure fluid flow and eliminate liquid buildup. These prevent a structural attack by stabilizing the protective skull, and protective skull is have a lot of role as we have discussed regarding the sensors feedback to the operators, and accordingly operators draws or simulate the profiles of the wear and tear in the hearth. So finally we verify and adjust using AUE and deep thermal sensors, feeding that data back into our operations. Unprecedented longevity is achieved only when operational execution directly protect the structural boundary